Imagine a weapon traveling at 1 mile per second. By the time enemy radar detects it, the missile has already covered 20 miles. By the time defensive systems calculate an intercept solution, it's 60 miles closer. By the time countermeasures deploy, it's too late. The target is gone. This isn't science fiction. This is hypersonic warfare, and it's rewriting every assumption about modern combat. In 2023, Raytheon Technologies announced a breakthrough in their hypersonic attack cruise missile program. The system had achieved sustained flight at Mach 5, 5 times the speed of sound, or roughly 3,800 miles per hour. But speed is only part of the story. These weapons maneuver unpredictably, fly at altitudes that confuse traditional defenses, and can strike anywhere on Earth in under an hour. Russia and China have already deployed hypersonic systems. America is racing to catch up, and Raytheon is leading that race. Today, we're breaking down the technology behind the fastest weapons on Earth and why they're changing everything we know about warfare. Let's get into it. Hypersonic weapons represent the most significant revolution in missile technology since the Cold War. They occupy a unique space between traditional ballistic missiles and cruise missiles, combining the speed of the former with the maneuverability of the latter. The result is a weapon that current defense systems simply cannot stop. Raytheon, one of America's largest defense contractors, has invested billions into developing these systems through programs like HACM, the Hypersonic Attack Cruise Missile, and various other classified initiatives. In this deep dive, we're going to explain exactly how these weapons work, from the air-breathing scramjet engines that power them to the thermal protection systems that keep them from melting at Mach 5. We'll examine what makes them so difficult to defend against, why they cost hundreds of millions to develop, and what their deployment means for global military balance. By the end, you'll understand why every major power is pouring resources into hypersonics, and why the Pentagon considers them a critical national security priority. Let's start with the fundamentals. The pursuit of hypersonic flight isn't new. It started in the 1960s with the X-15 rocket plane, which reached Mach 6.7 and gave engineers their first real data on hypersonic aerodynamics. NASA continued hypersonic research for decades, primarily focused on spacecraft re-entry and potential hypersonic passenger aircraft. But the military applications remained largely theoretical until the 21st century. What changed was the realization that traditional missile defense was getting too good. American systems like Patriot and THAAD could reliably intercept ballistic missiles. Aegis destroyers could track and engage threats hundreds of miles away. Russia and China faced a problem. Their strategic missiles might not penetrate American defenses in a future conflict. Their solution was to develop weapons that flew too fast and maneuvered too unpredictably for those defenses to handle. Russia tested the Kinzhal air-launched hypersonic missile in 2018. China revealed the DF-17 hypersonic glide vehicle in 2019. Suddenly, America's multi-billion-dollar missile defense architecture was obsolete against a new category of threat. The Pentagon's response was urgent. In 2018, hypersonic development became a top modernization priority. Contracts flooded to major defense firms, with Raytheon, Lockheed Martin, and Northrop Grumman all competing for programs. Raytheon's approach focused on air-breathing cruise missiles rather than boost glide vehicles, betting on scramjet technology that had been in development for decades but never successfully weaponized. By 2023, that bet was paying off. Now let's examine the actual technology that makes it work. To understand Raytheon's hypersonic missiles, you need to understand 3 core challenges: propulsion, thermal management, and guidance. Let's break down each one. First, propulsion. Conventional jet engines stop working around Mach 3. The air entering the engine is moving so fast that it can't be efficiently compressed and combusted. Traditional scramjets, supersonic combustion ramjets, solve this by allowing air to remain supersonic throughout the combustion process. But making a scramjet that actually works outside a laboratory has been the holy grail of aerospace engineering for 60 years. The tolerances are insane. Fuel must inject and combust in an airflow moving at thousands of miles per hour. The combustion chamber must maintain pressure despite supersonic flow. And the entire system must transition smoothly from subsonic launch speeds to hypersonic cruise velocity.
Raytheon's HACM uses a dual-mode scramjet developed with Northrop Grumman, revolutionary for its engine operating in ramjet mode during acceleration, then transitioning to scramjet mode for sustained hypersonic flight. This gives the missile flexibility traditional scramjets lack, allowing it to be launched from conventional aircraft at subsonic speeds, accelerate through the transonic region, and then punch through to Mach 5+ for the terminal phase. The fuel is likely a hydrocarbon blend, possibly JP7 or a derivative, chosen for its thermal stability and energy density. The air intake geometry is critical. It must slow incoming air just enough for combustion without creating so much drag that the engine can't maintain thrust. Now, thermal management. At Mach 5, aerodynamic heating is catastrophic, with the nose cone and leading edges experiencing temperatures exceeding 2,000 degrees Fahrenheit. Raytheon's solution involves multiple layers of protection, with the outer skin using ultra-high temperature ceramics, materials originally developed for spacecraft re-entry. Beneath that is an insulation layer to protect internal electronics and fuel systems. Critically, the missile likely uses fuel as a heat sink, circulating it through channels in the airframe to absorb heat before it reaches the combustion chamber. This is called regenerative cooling, and it's insanely complex to engineer. The fuel system must simultaneously cool the airframe, feed the engine at precise rates, and avoid pre-ignition from the absorbed heat. Then there's guidance and control. Traditional control surfaces, fins, rudders, ailerons, become problematic at hypersonic speeds, as moving them creates shock waves that destabilize flight. So hypersonic missiles use a combination of techniques: small adjustable surfaces for minor course corrections, thrust vectoring to adjust the engine's direction, and in some designs, reaction control thrusters for fine-tuned maneuvering. The onboard computer must process sensor data and adjust the flight path in milliseconds. Any delay, and the missile overshoots or tumbles out of control. Raytheon's HACM reportedly uses a combination of GPS, inertial navigation, and terminal guidance seekers. GPS provides course positioning but is vulnerable to jamming, while inertial navigation uses gyroscopes and accelerometers to track the missile's position, but accumulates error over distance. The terminal seeker, possibly infrared or millimeter wave radar, provides final targeting in the last seconds of flight. The challenge is making these systems survive the thermal and vibrational environment of hypersonic flight. Electronics must be hardened against heat, shock, and the intense G-forces of high-speed maneuvering. The missile body itself is a marvel of materials engineering, likely a composite structure combining titanium alloys for structural strength, carbon-carbon composites for high-temperature sections, and advanced ceramics for the most extreme thermal areas. Every gram of weight matters. The missile must be light enough for aircraft to carry, but robust enough to survive hypersonic flight. Raytheon has reportedly achieved a range exceeding 500 miles, which is impressive for an air-breathing system. Boost glide vehicles can go farther, but they can't maneuver as much during flight. Cost is the final technical consideration. Each HACM unit is estimated to cost several $1 million, possibly exceeding $10 million for early production versions. That's orders of magnitude more expensive than conventional cruise missiles, which run a few $1 million at most. But the Pentagon's calculus is that one hypersonic missile can accomplish what dozens of conventional missiles might fail to achieve: guaranteed penetration of advanced defenses and destruction of time-sensitive, high-value targets. So how would Raytheon's hypersonic missiles actually be used in combat? Let's walk through realistic scenarios and examine why these weapons are changing military planning. Scenario 1. Anti-ship warfare. Imagine a conflict in the South China Sea. A Chinese carrier battle group is operating 600 miles from a US base. Traditional anti-ship missiles like the Harpoon take nearly an hour to reach the target, giving ample time for detection and countermeasures. A hypersonic missile covers that distance in under 7 minutes. By the time the carrier's defensive systems engage, the missile is seconds from impact. Even if they detect it early, hypersonic weapons maneuver unpredictably, making intercept calculations nearly impossible with current technology. The carrier's billion-dollar defensive suite becomes irrelevant. Scenario 2. Time-sensitive targeting. Intelligence identifies a high-value target. Enemy leadership, mobile missile launcher, critical command node. The target will relocate in 30 minutes. Traditional strike packages take hours to organize: planning, aircraft launch, transit time, target confirmation. A hypersonic missile launch from an aircraft already in the area strikes before the target moves. This compresses the kill chain from hours to minutes, fundamentally changing how responsive fires operate. Scenario 3. Suppression of enemy air defenses. Before strike aircraft can operate safely, enemy air defense systems must be neutralized. These systems, advanced S-400s, S-500s, integrated networks of radars and missiles, are specifically designed to stop traditional attacks. They track cruise missiles easily and engage them at distance. But against hypersonic weapons moving at Mach 5 and maneuvering unpredictably, these systems struggle. The radar may detect the missile, but by the time the fire control computer generates a solution and launches interceptors, the hypersonic weapon has already maneuvered out of the engagement envelope. Even if an interceptor is launched, hitting a target moving at 1 mile per second while also maneuvering is exponentially harder than intercepting a ballistic missile on a predictable trajectory. The effectiveness question comes down to this: can current defenses stop hypersonic weapons? The short answer is no, not reliably. The United States is developing systems like the glide phase interceptor specifically to counter hypersonics, but they're years away from deployment. Russia and China face similar challenges defending against American hypersonics. This creates a period of strategic instability where offense dramatically outpaces defense. But there are limitations. Hypersonic missiles are expensive, so they'll be reserved for high-value targets. They're also complex, meaning reliability is a question mark. Early test results show success rates around 50 to 60%, which is actually impressive for cutting-edge technology, but means you might need multiple missiles to ensure target destruction. And despite their speed, they're not invisible. Advanced space-based sensors can track hypersonic weapons throughout their flight. The challenge isn't detection, it's interception. The real-world implication is that hypersonic weapons make deterrence more fragile. If both sides have missiles that can strike with minimal warning and penetrate any defense, the premium on preemptive strikes increases. Launch on warning becomes more tempting. Crisis stability decreases. This is why arms control advocates are pushing for agreements to limit hypersonic deployments, while military leaders argue they're essential for maintaining advantage. Raytheon doesn't care about that debate. They're engineering the weapons. Policy is someone else's problem. Let's assess what Raytheon has actually achieved and what it means going forward. The hypersonic attack cruise missile represents a genuine technological breakthrough. Sustained scramjet flight at Mach 5 is something only a handful of programs worldwide have accomplished. The integration of propulsion, thermal protection, and guidance into a weapon that can be carried by existing aircraft is engineering at the highest level. Compared to competitors, Raytheon's air-breathing approach offers advantages and disadvantages. Boost glide vehicles like Lockheed Martin's HACM 183 RRW reach higher speeds, potentially Mach 20, but they follow more ballistic trajectories. They're faster but less maneuverable. Raytheon's scramjet missiles are slower but more flexible. They can cruise at hypersonic speeds, loiter in a target area, and execute complex flight profiles. For tactical strikes against moving targets, the scramjet approach may actually be superior. The verdict? Raytheon has delivered a weapon that changes the calculus of modern warfare. It makes expensive defensive systems obsolete. It compresses decision timelines. It enables strikes that were previously impossible. But it also costs a fortune, exists in limited numbers, and kicks off an arms race with no clear endpoint. From a technological standpoint, it's a triumph. From a strategic standpoint, it's deeply destabilizing. Welcome to the future of conflict. Hypersonic missiles aren't the future anymore. They're the present. Raytheon's HACM is moving toward full production. Russia and China are expanding their arsenals. Every major military power is investing billions in the technology. And the physics haven't changed. Defense still lags far behind offense in the hypersonic realm. What does this mean for you? It means the next major conflict will be faster, more lethal, and less predictable than anything in history. It means that billion-dollar platforms like aircraft carriers might suddenly be vulnerable in ways they haven't been since World War II. It means the balance of power is shifting in real time, and most people have no idea it's happening. If you want to stay ahead of the curve on military technology and understand the weapons that are reshaping global security, subscribe to Military Contracts. We break down the systems, explain the technology, and analyze what it means for the future of warfare. Hit that notification bell so you don't miss the next breakdown. Thanks for watching, and I'll see you in the next one.